Hello friends, I Deepak Prajapati welcome you on my channel Engineering Mathematics DJ Ganit. In last lectures we have discussed Charpit's method for solving nonlinear partial differential equations of first order. But as we have seen that Charpit's method is very lengthy and sometimes it may become complicated if we are not able to solve Charpit's auxiliary equations by combining appropriate fractions. So to overcome that difficulty, we are having some standard forms of first order nonlinear partial differential equations, that if our partial differential equation of first order is in some particular form, then we have some shortcut methods to solve or to find out complete integral of that type of standard forms of nonlinear partial differential equations. So in this lecture and in upcoming 2 to 3 lectures, we are going to discuss those standard forms of nonlinear partial differential equations of order 1. So let us try to discuss those standard forms starting from first standard form. So the first standard form is, if given equation contains only P and Q, that means X, Y, Z are absent in given equation, then we can write given equation as function of PQ equal to 0. So if only P and Q are present, then this is the first standard form. So if your partial differential equation is in this standard form, then its complete integral is given by this equation z equal to ax plus by plus c. So this can be derived using Charpit's method, but we are not going into the details of the proof that how this equation 2 has arrived. We will just remember that if our partial differential equation is in this form, then its complete integral is given by z equal to ax plus by plus c. Now in this equation 1, independent variables are x and y. So there are only two independent variables, and by definition of complete integral, the number of independent variables and the number of arbitrary constants must be same. So here we are having 3 arbitrary constants. So we require only 2 arbitrary constants. So to remove one arbitrary constant, we have to substitute small p equal to small a and q equal to b in equation 1, and we will obtain function of ab equal to 0. So using this relationship between a and b, we can express either b as a function of a, or we can express a as a function of a, depending on the given problem. So suppose we express b as a function of a, then we will replace small b in this complete integral by function of a, and this is the complete integral of given equation, which is in standard form f of pq equal to 0. So if your equation is in this standard form, you can directly find out its complete integral, and you have to remember that if our equation is in this standard form, function of pq only equal to 0, then its complete integral is given by z equal to ax plus by plus c, where these constants a and b are related by the equation f of ab equal to 0, which is obtained by taking small p equal to a and small q equal to b in equation number 1. So let's try to understand this shortcut method using this equation, using this example number 1. We are asked to solve this partial differential equation, which is non-linear. You can see it is product of derivatives is present, so this is non-linear, and this k is fixed constant. So in this equation we can see only p and q are present, so we can apply that shortcut method. This equation is in standard form 1, so we write given equation is p into q equal to k. So because it is in standard form 1, standard form 1 is function of pq equal to 0, so we can rewrite 1 in this form also, both are the same thing. So because it is in standard form 1, we can directly write its complete integral. The complete integral of given equation 1 is z equal to a into x plus b into y plus c, where we can find out relationship between a and b by taking p equal to a and q equal to b in equation 1. Okay, so if I put p equal to a and q equal to b, I obtain a into b equal to k, and from this either I can write b in terms of a or a in terms of b. Suppose I write b in terms of a, so therefore the complete integral will be z equal to ax, b is replaced by k upon a y plus c. So this is the complete integral of given equation, in which instead of two arbitrary constants we have, instead of three arbitrary constants we have now only two arbitrary constants. Okay, so we give this number 2. This is the complete integral of given equation, where this a and c are arbitrary constants. Now in this example you are asked to solve the partial differential equation. So whenever you are asked to solve the partial differential equation, then it is not enough that you just find complete integral. You must find singular as well as general integral also if they exist. So if the question is like solve the partial differential equation, then we must find out complete, singular and general integrals. So here we now try to find out singular integral. So as we know, singular integral can be obtained from complete integral by eliminating arbitrary constants, and to eliminate arbitrary constant we have to differentiate complete integral with respect to arbitrary constants. So here 2 is complete integral, so we differentiate equation 2 partially with respect to constants a and c. So differentiate 2 partially with respect to a and c respectively, we obtain. So first we differentiate with respect to a. There is no a on left hand side, so derivative is 0. Derivative of z with respect to a is 0. Derivative of a into x with respect to a. So here x is constant, derivative of a is 1. So it is x. For second term we have k into y constant, derivative of 1 by a is minus 1 by a square. So we can write minus ky divided by a square, and the derivative of c is 0 with respect to a. and if we differentiate with respect to c, then derivative on left hand side with respect to c is 0 here also, because we have only z on left hand side, and on right hand side derivative of ax plus ky upon a, derivative of first two terms with respect to c is 0 and derivative of c is 1. So what we obtained here, 0 equal to 1. So this is not possible. So we obtain contradiction, which is impossible. So that means singular integral does not exist, or there is no singular integral for given equation. Of given equation 1. Now we try to find out general integral. So next one is general integral. So to find out general integral, again we are using complete integral, and as we know by definition of general integral, we have to assume that one constant in complete integral is a function of the another constant. So here there are two constants, a and c. So suppose we assume that c is function of a. So we write in equation 2, that is in complete integral, in 2 we take c as a function of a. Suppose c equal to psi of a, then 2 becomes, if we take c as a function of a, then 2 will be z equal to ax plus ky by a plus psi of a. Z equal to ax plus ky by a plus c, and c is replaced by function of a, and suppose we give it number 3. Now we differentiate number 3 partially with respect to a. Okay, because we want to eliminate arbitrary constant a. So again there is no a on left hand side, so we have 0 equal to x, derivative of ax with respect to a. Similarly derivative of 1 by a is minus 1 by a square, and k into y is constant, and this we write as side as a. This is ordinary derivative because psi is function of only one variable a. So now general integral can be obtained by eliminating arbitrary constant a from equation number 3 and 4. Here we don't know what is this arbitrary function of a, so we are not able to eliminate a. So what we can do is we can simply write down general integral can be obtained by eliminating arbitrary constant small a from 3 and 4. So this is the way how we solve the nonlinear partial differential equation of first order. So we have to check whether singular and general integrals exist or not. So now we move to the next problem. Find complete integrals of following partial differential equations: p square plus q square equal to 1 and p plus q equal to pq. So here we have to find out complete integral only. So it is specified that we have to find out complete integral. So in part A, given equation is p square plus q square equal to 1, and you can observe this is in standard form 1, only p and q are present. So therefore the complete integral is as we know, complete integral is given by z equal to a into x plus b into y plus c, and to find out relationship between a and b, we have to take small p equal to a, q equal to b. In 1 we have a square plus b square equal to 1. So from this we can write either a in terms of b or b in terms of a. So therefore b square is 1 minus a square, and therefore b is plus or minus square root of 1 minus a square. So we substitute this value of b in complete integral 2. So therefore the complete integral is z equal to a into x plus or minus square root of 1 minus a square into y plus c, and a and c are arbitrary constants, where a and c are arbitrary constants. So it is simple, you just have to identify whether it is in standard form 1 or not. Second equation is p plus q equal to pq. So you can see this is also in standard form. We give it number 1. So complete integral is given by z equal to a into x plus b into y plus c. Now I am not writing all the details. So this is the complete integral of equation number 1, and if we put small p equal to a, small q equal to b in 1, we have a plus b equal to a into b. So this I can rewrite as a equal to ab minus b, and if we take b common, we have b into a minus 1. So this gives me b as a function of a. So if I substitute value of b in equation 2, I will obtain the complete integral. So therefore the complete integral is z equal to a into x plus a by a minus 1. This is value of b plus c, where a and c are arbitrary constants. So it is easy to find out the complete integral if our equation is in standard form 1. Now there are some partial differential equations which are not in standard form 1, but they can be reduced in standard form 1 by making some appropriate transformation of variables. So let us try to understand this with the help of example. Find the complete integral of x square p square plus y square q square equal to z. So we start with this given equation. Given equation is x square into p square plus y square into q square equal to z. Now I want to reduce this in terms of standard form 1. So for that, first I divide by z, and I write p square as square of del z by del x. Same thing on this side, y square divided by z, del z by del y. Q is replaced by del z by del y equal to 1. This we can write again as x divided by square root of z del z by del x whole square plus y square root of z del z by del y whole square equal to 1. Now from this you can observe, if I compare, suppose my new variables are capital X, Y and Z, then which transformation I have to consider such that small x, y, z and capital X, Y, Z are related. So I will obtain that idea from this. Suppose this is equal to del capital Z by del capital X. Then from this you may have the idea that I should consider x upon del x. This be considered as 1 by del capital X, and this second part del z upon square root of z must be equal to del capital Z. Same thing here also, we must have y upon del y equal to 1 upon del capital Y, and del z upon under root z equal to del capital Z. So from this we may have a rough idea that which change of variables will work to convert given equation into standard form. So if I take x by del x equal to 1 del capital X, y upon del y equal to 1 upon del capital Y, del z by under root z equal to say del capital Z, and this I can rewrite as del capital X equal to del x by x, del capital Y equal to del y upon y, and del capital Z, this I can rewrite as z to the power minus 1 by 2 del z. So from this if I integrate both sides, this is going to be capital X equal to log x. Same thing for these two, capital Y is log y, capital Z is z to the power minus 1 by 2 plus 1, which is z to the power 1 by 2 divided by 1 by 2, that is 2, or we can rewrite this as 2 times square root of z. So now if we substitute these values in this equation, suppose it is equation number 1, suppose this equation is equation number 1. So if we use this change of variables in equation 1, then we will have del capital Z by del capital X square plus del capital Z by del capital Y square plus 1. So therefore equation 1 Therefore 1 becomes del capital Z by del capital X whole square plus del capital Z by del capital Y whole square equal to 1. So now this contains only partial derivatives with respect to capital X and Y, so that I denote by capital P and capital Q, where capital P is nothing but del capital Z by del X and capital Q is nothing but del capital Z by del capital Y. Now to solve this equation, as I discussed, it is in standard form 1, so therefore the complete integral is instead of small z I have to use capital Z equal to small a into capital X plus small b into y plus c. Therefore, if now we substitute capital P equal to small a, capital Q equal to small b, so where a and b are related by this relationship, where a square plus b square equal to 1, and this implies b square equal to 1 minus a square, and therefore b is plus or minus under root 1 minus a square. So if we substitute value of b here, and then the complete integral is capital Z equal to a into capital X plus or minus square root of 1 minus a square into capital Y plus c. And now capital Z is 2 times square root of Z, and these two are log x and log y. So therefore 2 times under root Z equal to a ln x plus under root 1 minus y square, capital Y is ln y plus c.